all right? So entropy changes accompanying specific processes and how to calculate those. So we actually already talked about expansion, but I'll just give you a reminder, I'll give you a review on this. We know this starts with the thermodynamic definition of entropy, which says delta S equals the integral from initial to final conditions of dq reversible over temperature. And then obviously we've got to say, we've already said dq, right? So dq divided by t, okay? And so we know that reversible work will equal negative reversible heat, right? They're equal and opposite. Okay, and work supplied reversibly is negative nRT, natural log VF over VI, which means Q reversible is positive nRT, natural log VF over VI, okay? And thus, when we plug this in, okay, and we take dq of that, and we integrate it, divided by t, then that leaves us with delta S for expansion is just nR divided by natural log of VF over VI, okay? And here you can see this plot. This is showing you in this reduced variable space, right? So on the x-axis, it's showing you the ratio of VF over VI. And on the y-axis, it's showing you delta S divided by nR. So really, you're just seeing the logarithmic relationship there, okay? And so, of course, that relationship, so this is just using the ideal gas situation, but when we use real gases, right, we get different curvatures, okay? And that's related to those heat capacity ratios, those gamma ratios. I don't really want to spend much other time talking about that, other than just kind of reviewing how I can put together calculating, entropy of expansion based on the other equations that I know. Okay, folks? So that's really all that I'm going to say there. All right?